right, we are looking at section 6.2, page 378. If you are not typically in the habit of getting your book out and looking at it, you will definitely want to do that. I have taken several images from the textbook and put them into our notes, but there are lots of other images in the book that will make this much easier for you to see. Ladies especially, we have a harder time seeing in 3D than the guys do, so you'll want to rely heavily on diagrams and drawing. Hopefully you are a better artist than I am. I don't really see how you could be a worse artist than I am. And so when you're drawing these out, if you're having trouble envisioning them, feel free to come grab the solutions manual and look at the diagrams and look at the drawings. I'm going to run the homework for you almost every day because it has all the diagrams and the drawings on it that make it a little bit easier for you to see and make this a little more concrete for you. Okay, so let's look at page 378, volume. There are actually two different ways that you can calculate the volume of these figures that we're going to be working with. One of them is in 6.2 and one of them is in 6.3. It's two different methods for doing the same thing. AP requires the method in 6.2. It does not require the method in 6.3. We learn 6.3 just because it makes our life easier to have some options and to have some choices. Okay? So when we're talking about finding the volume of a solid, all right, let's say that you wanted to calculate the volume of an everyday object like a loaf of bread, okay? We've learned that volume is area of the base times the height. Like, let's say you're trying to find the volume of a box, right? It's length times width times height. Why is that? Well, because the area of the base is a rectangle, so length times width times height. That's where we get our volume formulas. So if I wanted to find the volume of an abstract figure, like a loaf of bread, what I would want to do is I would want to find the area of the base times the height. So let's start with finding the volume of just one slice of bread. Okay, let's take this on a little smaller scale. If I wanted to find the volume of one slice of bread, I could cut down through my loaf and get my little slice of bread here and lay it out on the countertop. And this would be its surface area, and its thickness would be its height, right? So I could say if I wanted to find the area of the base, it would just be this surface area times its thickness, its height. So if I found the volume, then it would just be the area times its thickness, its height, its change in x. And once I knew the volume of one slice of bread, then I could go through and I could say, okay, if I found the volume of this slice and the volume of this slice and the volume of this slice and this one and this one and this one and this one, and I added them all together, that would give me the volume of the whole loaf, right? And so that leads us to the idea of volume and the definition that they give us here in section 6.2. If we started right here at A and we added the volume of the first slice with the volume of the second one and the third one all the way down this loaf until we got B, it would be the summation of the volumes of each of those slices of bread that would give us the volume of the total loaf. And so what we could say is that volume is equal to the summation from A to B of A of x dx, where this is representing the volume of 1 and this is the summation of all the volumes all the way along that loaf of bread or whatever our figure might be. Okay, so look at example number 1. For example number 1, it says we don't want the example 1 in the textbook. Over on page 381, example 2 out of the textbook is our first example here. It says find the volume of the solid obtained by rotating about the x-axis the region under the curve y is equal to the square root of x from 0 to 1. Find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals the square root of x from 0 to 1. Let's start with that last piece, region under the curve y equals square root of x from 0 to 1. So here's y equals square root of x, right? That's just our regular root function. And we just want to start at 0 and stop at 1. So that would be the piece of the graph we want. And it said the area of the region under that curve. So if I'm looking for the region under that curve, that's just this blue piece right here, right? Then it says, take that figure and revolve it around the x-axis. So that's what this little symbol right here means. I'm revolving around the x-axis. So if I took this little two-dimensional figure and I revolved it around the x-axis, it would create this three-dimensional figure. Now, something that might help you in graphing in 3 dimensions and visualizing this, there are tons of online free 3D graphing models. That's where this guy came from down here. I just went into Google and searched for one, put my equation in, and it was really cool when this came up because I was able to click on it and turn it. I could look inside of it. I could look at it from the top and the bottom and sides and that type of thing. So if that would help you envision it, you might want to use a resource like that. So here's the figure that I want to find the volume of. Remember, we said volume is going to be the integration from a to b of a of x dx. All right, so let's start with what is a of x. If I cut a cross section of this, just like we cut our slice of bread up here, if I cut a cross section of this, you'll notice that cross section is a circle. So I need to find the area of that circle. Area of a circle is pi r squared, so if I could just find the radius of that thing, then I would know the area of the cross section. All right, so if I'm trying to find the radius, I'm going to start right here at the x-axis and go straight up. That radius then is a straight up vertical value. It's going to be the same thing as my y value. And remember, this equation was y is equal to the square root of x. So it'd be like saying the square root of x minus 0 if I did top minus bottom like we did yesterday. And so my radius would be the square root of x. So now I've got pi square root of x squared. Square root of x squared would just give me x, so my area is pi x. So remember, we said that if we took our area, pi x, and we thought of the dx as kind of like our change in x, our height, then this could represent the volume of that one cross section. I want to go back then and I want to say, okay, I need the volume of this cross section and this one and this one and this one and this one, and then I need to add all of those up. And so the way that I could represent that would be the summation starting here and going to here. So this value was 0 and this value was 1. So that's what I want to use for A and B. So we've got our setup. For this test, your answers will be setup only. So that would be your answer. You would not need to finish working it out. You would be done there. Now, we did this entire setup using just common sense and looking at the figure. And we'd like to rely on that as opposed to memorizing some facts, because our facts are going to change from section 6.2 to section 6.3, but our common sense and figures will not lie to us. However, if I'm working with the method of section 6.2, finding the volume by disks, if I'm revolving around the x-axis or any other horizontal axis, like maybe I'm revolving around y is equal to 2 or y is equal to -5 or something like that, any horizontal axis, everything is going to be in terms of x. My a value, my b value, my function, and dx. Notice it laid itself out that way without us even knowing that. Also notice that we're going to do top minus bottom. Yep, we did that over here without even knowing it. And something that'll be a helpful reference for us is that our radius is going to be perpendicular to our axis of revolution. So since they told me to revolve around the x-axis, I knew my radius was going to be perpendicular to that. Okay, so those are things that can help us, but again, we don't want to memorize them and rely on them, because when we get to section 6.3, a lot of those things will change, and it's easy to get confused as I'm not relying on my figures. All right, what if I weren't revolving around the x-axis? What if I were revolving around the y-axis? If we look at example number 3, it says find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So before we start trying to revolve anything, let's draw that figure, okay? So they told me I've got y is equal to x cubed. So here's that figure right here. Y is equal to x cubed. Y is equal to 8. and x is equal to 0, which is the y-axis. So we said yesterday when we were trying to find the bounded region, think about it like a fence in your backyard. What just got fenced in by those three drawings? So I've got this one, and this one. So this little blue region right here is what just got fenced in. That is my bounded region. All right, we want to take that bounded region, and this time they've asked me to revolve it around the y-axis. So if I revolve it around the y-axis, this is what I'm going to come up with, or again, this is one of those images that I pulled from offline from a 3D grapher. So here is my figure. And again, if I draw a cross section of this, because again, if you think of this like a loaf of bread, I'm going to do a cross section here, and here, and here, and here, and here, all the way along. And so if I look at this cross section, it's a circle, so I need to find the area of that circle, and area of a circle is pi r squared. So I need to figure out what my radius is. So I come back up here. Remember we said the radius is perpendicular to the axis of revolution, and that makes sense because we were revolving around the y-axis and our radius would be perpendicular to that. So if I want to find this horizontal value, I'm going to need to do this right-hand value minus this left-hand value, just like we did yesterday. In this particular case, my right-hand value is just x value of, and the x function was y to the 1/3. And then over here, this is x equals 0. So I'm going to do y to the 1/3 minus 0. And so my radius will be the exact same thing as my x value. And my x value, my x function is y to the 1/3. All right, so if I square that, y to the 1/3 squared is going to be y to the 2/3. So my area will be pi y to the 2/3. So let's bring that over here and replace area with pi y to the 2/3. And then we've got our dy. And again, that was one cross section, but I would want to go through and cut a piece here, and cut a piece here, and cut a piece here, and here, and here, and here, and then sum all those up. And so you'll notice the sums that I'm looking for this time are going up the y-axis, so I would want the y values from 0 to 8. And that follows suit with what they tell me up here. When we laid this out by common sense, notice that everything ended up being in terms of y. Our upper and lower limits of integration, our equation was in terms of y, and we had that dy on the end. We also, to find our radius, did right minus left, and our radius was perpendicular to the axis of revolution. So again, this setup will be your final answer when we do our test, but I did go ahead and work that out for you so that you could see it. All right, no need for us to do a million of these tonight. I think 3 is good to get us started, and we'll be working on this section again tomorrow as well. So on page 387, we're doing 135, challenge 9. Page 387, 135, challenge 9.